First one.
Why did you see it?
Hello? We're getting there. Couple more. Jordan and Emma. Let me see.
Andrew, has anyone told you that you're a beast?
You'd be the first, Nate.
Yeah.
Says
Okay.
right there on the shirt.
Yeah, just making sure.
All right, I guess we'll start. Oh yeah. So I have practice questions for you on my open math. There's Jordan. I've got some practice questions on my open math that you guys can check out. Down at the bottom. Oh well, there's two of them. Don't worry about the hypothesis tests. I didn't put any questions in there yet. But the proportions practice.
Where do we go to find it?
My open math is at the bottom.
The confidence intervals?
It's proportions.
Or below that? Oh, proportion practice, hypothesis test.
Yeah.
Just the proportion one?
Yeah.
Got it. 5 questions, that's it?
Yep.
Can we do it as a class or no?
Yep.
Individual.
Well, you have your own versions, but it should be the same type of thing.
Got it.
So I'll show mine, and then your guys' should work the same. And we got everybody. Oh no, still not Emma. All right, so if you see my first question, new fertilizer was applied to the soil of 24 bean plants. 58% of them showed increased growth. Find the margin of error and 95% confidence interval for this statistic. Round all answers to 2 decimal places. So these ones are proportions. They work just like what we had done before with confidence intervals and the sampling distribution questions. But now instead of mean values, we're going to use proportions. So it's slightly different, but it's pretty much the same thing. So we want to build a confidence interval. If you remember, I'll write your formulas. Your confidence interval will be, let me get my little glove. Whereas before, you would take your X bar and you would plus or minus your margin of error, where your margin of error was the standard error, which is sigma divided by the square root of the sample size, times some critical z-score based on how confident you want to be. Now we are working with proportions, so the middle of our mean value essentially is going to be our p hat, our proportion that we have. That's going to be our center of this distribution or this interval. And we're going to add or subtract the margin of error, which in this case is the critical z-score still, times sigma over the square root of n, just like before. The difference being that for the sigma value, we are going to use the square root of the p-value times its complement. So you just use the p-value a bunch of times. Okay? So back to the question. So we have 24 bean plants. So that's going to be my sample size. 0.58 will be the center of my confidence interval. That's like my mean value was. That's what I got as my proportion. And then to create the margin of error, I need the z-score for 95%. I need to calculate the standard error and multiply those. So for, what is does anybody know the z-score? Why did I do X? For 95%?
Isn't it like 2.5 something?
I don't think it's 2.5.
Online it says 1.96.
Oh, I was close.
Yeah, there you go. 1.96. What did they say about? I think they said 2 decimal places. All right, so then you have your standard deviation is going to be, well, our p hat was 0.58. Our standard deviation is going to be 0.58 times what?
1 minus 0.58.
Yeah, what does that give me?
I got 0.4935.
After you did the square root?
Yeah.
Okay. Then you'll have to divide that by the square root of the sample size. And then multiply that by your z-score. That should give you your plus or minus margin of error, this margin of error.
Wait, what was your wasn't yours like 30 or something? However many beans you had or whatever.
Yeah, like 20, 24. So altogether I'd do that'd be my margin of error.
You times it by the confidence by 1.96.
Yeah.
I got 0.197 for you.
Yeah. So that means my range would be 0.58 plus or minus 0.197. So I got like 0.777. And 0.383. Is that okay?
Wait. How do you put that in the my open math?
Well, let's see. So you're going to put the first number here. Oh, I guess they want percentages. So
Yeah, that's why I didn't want to put it in. And
sneaky.
very sneaky.
Are those the same numbers? No. Did I do that right? Mine's a little different. Yeah, mine came out a little different. Did I do 24? Let me check something. So 95.
Minecraft.
Did you get the same?
What?
Did you guys get the same?
Couldn't tell you.
I think I did something wrong with my square roots. We'll see. No, I got the same. I don't know why it's a little off. For some reason, theirs is a little different than mine. I got 0.197 here, not, well, 19.7, not 20.4. I don't know. Let me try to replace it or something. Oh, well. Let me refresh, maybe. Let me see if I get the same numbers here.
I think we just skip question 1 because I got it wrong too, and I did the same thing.
Yeah, this
You
is also
thought-
different than what I got. Let me just try one more thing.
Okay.
I'm going to put in all these decimals to see if that makes a difference. Nope. All right, yeah, skip number 1. I wonder why that is. Well, let's see number 2.
I think it's just dumb.
It might be programmed weird. But I think a lot of these are from the same author, so let's try them together, I guess. But this is the formula that you'd use. It's just like the other ones. Suppose you draw a single sample of size n from a large population and measure its sample proportion. The margin of error for 95% confidence is what is this one? You draw a single sample of size n. I don't even remember selecting this question.
Well, free answer, so that's all I'm saying.
I don't really get this one.
Yeah, I think it's dumb.
Let me refresh, because that what didn't look like what I chose just a minute ago. No, I don't know. I don't even remember picking this question.
So don't do 2 either. That's
Yeah.
We might as well just call it a day at this point.
No.
I don't know.
Well, I mean, these might be off because I think all these are like the same author, but
Brady might know. Brady.
I must have just checked the wrong box when I read one of the questions and then, because I don't even remember reading this. It's changing from 95% confidence interval estimate for population proportion to 99%. What happens to the confidence interval if you change from 95% confidence to 99? Do you think it get bigger or smaller?
Think it would. Actually, I don't know.
So here's your
Smaller?
formula.
Would it be smaller?
Here's your formula for the margin of error. That makes the confidence interval size, right?
It would be bigger.
You're going to pick bigger numbers for this Z
We like
star
it bigger.
when you have more confidence. I mean, if you just think about it intuitively, the bigger the range, the more confident you can be that you're going to have the value in that range.
So it's bigger by 4%.
No.
Oh, well, never mind.
What's the Z score for 95%?
1.96.
And what's the Z score for 99%?
I don't know. I think Andrew knows it.
Do you?
It is 2.58.
0.58?
Man, it's like he's in his own castle right now.
So if I change 1.96 to 2.58, what percent of an increase is that? You guys know how to do that?
A big increase.
Take the difference and divide by the old value.
About like
Right.
a 33%.
Probably about there, yeah.
31. Increase by 31.
Yeah, so if you do 2.58 minus 1.96, divide that by 1.96, you get about 32% actually.
This game is like too easy.
So you can do that one at least. That one's just radio buttons, so it's not that hard to pick the, you don't have to enter anything. All right, let's see how this one works out. A large candy company has a product that comes in several different colors. The company claims that the proportion of these candies are colored red is 23%. Suppose a random sample of 360 candies is gathered. Let p hat be the proportion of candies from the sample that are red. Okay, I'm just checking to make sure this isn't the next kind of question that we're going to do. For all parts, keep at least 4 decimals of precision. So that means up until the end, you need at least 4 decimals. You need like 5 decimals. And then at the end, you can round to 4. Find the mean of the standard deviation and the standard deviation of the p hat. So the mean is going to be your proportion. That should be. Your standard deviation should be that thing times its complement divided by the square root of the sample size. That's your sigma p hat. I think. Maybe I think that you divide by the square root of the sample size. Let's see. Yeah, and then divide by square root of 360. Yeah. So that works out fine. I don't know why that other question wasn't very good. Does that make sense?
What do you multiply the 0.23 by?
Here you're going to do the square root of 0.23, what, 0.77? And then divide by 360, all inside the square root. And again, this, another name for this is the standard error. Did that work? Good. All right, now you can build a normal distribution using the normal CDF, using this as your mean and this as your standard deviation. And they want, what is the probability that you'll get a sample that is less than 0.21? Which what did I say? 23? 360 was it? 0.27, or I don't remember. 0.21. So you guys get about 18.36, maybe.
How'd you do that?
You can just do a normal CDF.
Mm-hmm.
From -9 to
Infinity,
0.21, yeah.
or to whatever number they say.
Yeah. And then this is your mean, and this is your standard deviation,
What's your mean?
the 0.23.
I got it.
Yeah. Is that good? Okay. And the last one, you have 205 gun owners, 61%. They have it for protection. Find the margin of error in 95% confidence interval. So this is like number 1, I think. So let's hope it works. The margin of error should be the z-score, 0.196 times the square root. And then it's 61%. So I'll do 0.61 times 0.39 divided by 205. That one's correct. So yeah, that should give us a good margin of error. You guys get that? Any questions over this? It's a lot like what you did with the X bar, finding the standard deviation, finding the standard error, doing confidence intervals. You can do it with proportions too. When you have categorical data, and you have a sample of things that you've picked, the number of things that you're looking at is your sample size. The percentage that are a certain way is your mean. Your standard deviation for the population, you just take the decimals for the percentage times its complement, square root that. And then otherwise everything's the same. Is that good? Well, you get it, Nate? No?
I mean, I did, but it didn't give it to me, so you're gonna have to fix it.
What were your numbers?
All right, it was 6304. I got the margin of error right, but every single time I did the confidence interval, it didn't do it. So then I tried writing it like how it looked, and that's what I did. So,
Did you do it as a percentage?
well, yeah, I did.
Okay.
So it's right. It's just dumb.
Okay.
So towel's thrown in.
No, no, no.
Oh,
So we have more to talk about. I don't know how much we'll get to, but so one little activity I like to do with students at some point is ask you guys. So you're gonna have to answer. So this is just like conceptual right now. What are some scientific theories that you know are considered true today, that are true theories or are proven?
what do you mean by that? Like anything?
Yeah, ones that what theories do we have today that we know that we've proven are true?
Darwin.
Darwin?
Darwin's theory of evolution.
Any others? Is that the only one?
Newton's laws of physics, all that
Newton's
stuff.
laws. Anybody got anything else?
Not a good one.
What was that, Nate?
What?
What did you say?
You don't want to know. I forgot my mic wasn't muted. Backward.
All right. Well, it turns out that's a trick question. None of them have been proven true.
We got
Uh,
bamboozled.
Yeah. There's actually no such thing as scientific proof. So whenever you've heard that something has been scientifically proven, the person, I mean, that's like that can't happen. Nothing can be proven. Now, you know what they mean. You know that they just mean there's a lot of evidence, I guess. But there's actually no such thing as proving anything, scientifically speaking. You can have proofs in math. That means something different. Those don't really apply to the real world. That's just saying that if you have a system of logic and you make certain assumptions, you can derive some statements from other statements following a system of logic. That's what it means to prove something in math. That has nothing to do with the world.
So what you're saying is the Earth could be flat.
It could be. What scientists are able to do is disprove theories. That's all they can do. They cannot prove them. So there's no theory that ever was or ever will be that will have ever be proven. For example, Newton's laws have actually been sort of disproven. Einstein has replaced them wholly. In the past, Newton had theories of motion, and the way he could explain motion was in terms of separate forces. And then he had a separate theory of universal gravitation, which described the force of gravity. And if you apply the force of gravity to objects in his theory of motion, you could do pretty well at predicting how they'll move. It wasn't exactly correct. there are a number of ways in which it fails. So when things are moving very, very fast, these fail. And when things are very, very small, those laws fail. Or any combination thereof. Einstein has wholly replaced Newton's theories. So with Einstein's general relativity, he merged the laws of motion with gravity. In a sense, gravity has kind of taken over everything. The laws of motion are now just the shape of space-time. The way things move is determined by the shape of space-time.
This sounds like physics.
What's that?
So this just sounds like physics talk.
Yeah, these are theories from physics. It applies to Darwin's theory too. All theories. A theory is the best that you can have. Like, they never graduate to become laws. We just have some theories that have yet to be disproven. So in Einstein's theory, in Newton's theory, there were objects and there was a force that acted across space on these separate objects. But in Einstein completely replaced the underlying explanation. And now there's this intermediary continuum that we're all in, the arena, space-time. And the objects actually distort, I guess you could say distort. They affect the space-time around them. And it's because they share, they're in the same space-time as one another. The objects are not moved by forces from the other object. They follow the contours of their local space-time. So it's a completely different basis for the explanation. There aren't really the forces in Einstein's theory. So one thing to keep in mind is that in any science, we can perform tests. Whenever we perform tests of a theory, we're attempting to disprove a theory. And so what theories have to be able to do is prohibit certain observations. There have to be things that if your theory is scientific, you have to be able to make predictions from that theory that if you checked on that and you perform the experiment there have to be things that if you ever observed them, it would prove the theory wrong. That way it can be tested. So our best theories, like Einstein's theories, quantum theory, Darwin's theory, they are not proven, but they're also not disproven, and they have been extensively tested. Many attempts at disproving them have failed, and that's what makes them good. That's what makes them things that we can rely upon. But the second one experiment comes back disproving them, they're out the window. Now, usually, like is the case with Newton's theories to Einstein's, Newton's theories for hundreds of years were believed to be undisproven, that were believed to be the best we had. And then hundreds of years pass, and then they get disproven when we have better experimental technology. So, things can have a long run and then get disproven. But still, Einstein's equations are extremely complicated in very many situations. They're very hard to calculate, or maybe not even possible to calculate in some situations. So Newton's theories are very fine. They're very good. They're good in lots of situations, and they're easier to work with. So we still use Newton's theories all the time. We didn't need Einstein to go to the moon or whatever, put satellites. Well, we do actually use relativity when calculating things with GPS, but Newton's still pretty useful. So even when theories get proven wrong, that doesn't mean we stop using them. We just know that they're wrong. Like Bohr's model of the atom, we know that's wrong, but it's useful still. So we still teach it. So that's one thing to be aware of. So I guess the main lesson to keep in mind is that we cannot prove anything. We cannot confirm any theory to be true. There's no such thing as confirmation. What you should try to do is disprove. Look for things that could never happen if the theory were true, and then you can potentially disprove it. Or if it passes many, many tests of that sort, then it's considered reliable. Is that making sense so far? All right, so I'm going to give you a little preview to what we're moving into. This is kind of the heart of the statistics course. This is called hypothesis testing, or sometimes they're called significance tests. I'm going to share my screen again and draw for you. All right, so when we perform a hypothesis test, in a course like this, we always have two competing hypotheses. So here's how we could sort of write it. This is H with like a 0, and this is H with a subscript A. And the top one is called the null hypothesis, or the default hypothesis, whereas the bottom one is called the alternative hypothesis. And so whenever this, like somebody claims something, like the average student gets 6.5 hours of sleep a night, on average, we would want to test that claim. So we have different symbols. I'll say that mu is the true mean. It's the true average for the population. And it's generally not known. We try to estimate it, or we try to test claims about it. Mu sub 0, mu naught, is the claimed, guessed, or old previous value for the mean. So if somebody makes a claim, that's the mu naught. Or if last year's data indicates that the mean used to be a certain thing, that would be mu naught. And then mu would be the current value, or the new value, or the real value that we don't know. So one situation that we have when we do hypothesis testing is we want to test the idea that the true mean is equal to the claimed mean. So mu equals mu naught.
Mr. Sotelo?
Yeah.
Brady's computer died, he said.
Okay. I guess for good, or is he coming back?
I have no idea.
All right. Well, I'll post the video so he can catch anything he missed. So the default hypothesis, the assumption is mu is either equal to the claimed value, or mu is not equal to the claimed value. And these are typically opposites. So if one's equal, one's not equal. This is what the test you would run if you think, or you want to test that whether or not the the mean value, the true mean, is actually different than the claimed value. But you're going to assume that they're not different, that they're the same, that the claimed value is is accurate. So your default hypothesis is that they are the same still, whereas your alternative hypothesis will be that they are now different. Okay, does that make sense? So let's say someone claims that the mu naught is 6.5 hours of sleep on average. All right. Well, watch the end of the video, I guess, when you get the chance. Have a nice day. So let's say that somebody claims that all the students have, on average, sleep for 6.5 hours every night. So I'm going to assume as my default, as my null hypothesis, that the true mean is 6.5 hours. But my alternative hypothesis is that it is not 6.5 hours, that it's much more or much less, either one. So this is sort of like we call this a two-tail test because it could be greater or less than 6.5. We don't really care which side of it it's on. We just want to know if it's different than 6.5. Does that make sense so far to you guys? Are you guys following this? Okay. Another scenario you might be in is, let's say somebody claims that that the default hypothesis is that let's say we want to check to see if a number has gone up in value. So like the number of hours that people sleep on average, we think it's higher than it was last year. So the default assumption is that it's the same as the old value, but or less than. But usually the top one, the default hypothesis, always has a quality in it. And the alternative is always the exact opposite. So this would be that the true mean today is now greater than the claimed value. So if you wanted to test to see if it has gone up, and you're only caring about it going up, you're not really caring about it going down, you would perform this test between these two hypotheses. The alternative is kind of like what you're trying to see if it's changed like, but your default will be that it hasn't changed in that way. And the other one is that, you could say that the default hypothesis, maybe you think that the thing with the alternative hypothesis, you think it's now less than it used to be. So your default hypothesis would be that it's more or the same. So these are kind of like the three types of tests you could do. Is it different? But you assume that it's not. Different, positive or negative. Did it go up? Or did it go down? And so you're going to assume that it hasn't changed in that way. And then your test. So the thing is that you're going to assume that there isn't a change unless you have statistically significant evidence that it indeed has changed. So that's the kind of test we're going to perform. The idea here is that, like, if you think about this hypothesis test, the idea here, if I want to say that, I think the true mean is now different than the claimed value. And just like how you cannot confirm, you got to watch the language here. If you decide that you do have evidence that it's now different than it used to be, it's said that you now you can reject one possible outcome is that you reject the null hypothesis. So that's one of your options. Your other option, you would like to think that you have confirmed the null hypothesis if you do not find enough evidence to suggest that that there's a change. But this is never an option. You're never going to confirm something as true. You can eliminate it. You can say that I have significant evidence that it's not true. But if you do not have significant evidence that it's not true, that does not mean that you have significant evidence that it is true. It doesn't mean that it is true. So your options are reject the null hypothesis or fail to reject H0. These are your two options. You're not saying that it is true. You're just saying whether or not you have enough evidence to reject it, or if you do not yet have enough evidence to reject it. That doesn't make it true. It just means it survived this test. Does that make sense? Are we good with that? All right, so we will, next class, I will introduce to you the ways in which, there's different ways in which you can test hypotheses. And then, you know, once you guys get good with these different ways, we'll go back and talk about basic stuff, like how do you collect evidence in a fair way? You know, how do you get good data? All, you know, some basic concept type stuff. But once you learn how to test claims and stuff, you'll be ready to move on to projects where you can do your own little research project and see if you can come up with enough evidence to say whether or not you can make a statement one way or another. But we'll start with how to make these tests next class. That sound good? All right, any questions? Okay, well, you guys are free to go then. I will see you Thursday. That's our last day of school for the week.
Yeah, see ya.
Bye.